Hello everyone, my name is Brady and today me and my team will be reviewing the attitude determination and control system from the MUN-Killick-1 CubeSat project. We will primarily be going over the testing procedures we have developed for the ADCS system. The group members include myself, Anal Azad, Tariq Aziz, and Fernando Saenz. For context, MUN is taking part in the Canadian Space Agency CubeSat project. This consists of multiple teams from universities across the country developing CubeSat satellites. MUN's satellite is the Killick-1 and will be used for research into sea ice, primarily in the Arctic. Under the guidance of engineering professors and Seacor's Vice President of Remote Sensing, MUN's team of engineering students work until launch in 2020 to 2021 to design, build, and test a CubeSat space satellite. The satellite will be used to measure thickness of sheet ice and will be capable of data transmission to a ground station. Our team is developing the tools and processes necessary to test the satellite's attitude determination and control system, also referred to as the ADCS. The ADCS is responsible for the spacecraft's maneuvering capabilities. The ADCS is a critical component to the satellite, as if it fails after launch, the satellite becomes unable to complete basic functions and renders itself redundant. The project objectives consist of the following. Firstly, a testbed to evaluate the Killick-1 CubeSat's ADCS functionalities by simulating a space-like environment needed to be designed and manufactured. The designed and manufactured components include an air bearing, a bearing support structure, and an internal sphere structure that will be responsible for holding the satellite in during testing. The development of the test procedures necessary to fully test the maneuvering capabilities of the ADCS was this term's main focus, with most of the design and manufacturing being accomplished in Term 7. The testbed for the ADCS is primarily constructed of an air bearing, which is a non-contact system where air is used as a lubricant. A pressurized air system is used to generate lift. The previous ADCS testing team created a proof of concept design and 3D printed it out of mostly PLA with a bit of ABS used due to the material shortage because of COVID-19. This proof of concept was evaluated by our group and the basic design was kept with a few minor modifications. The design modifications for the bearing are as follows. O-rings and O-ring grooves were added to the structure to allow for a better seal. Horseshoes were added to the bolt holes to allow for better part and tool clearance. Threaded rod was sourced and used instead of long bolts as they were very hard to find and they were also expensive. Chamfers were added to various locations in the design to break sharp edges to allow for better fits between components, and the material was changed to Delrin, which is a sturdy plastic with a great machined surface finish. This material allowed for drastically less friction to be present in the model.
For validating the design, von Mises stress analysis was done in SolidWorks simulation. The material used for simulation was the same material that would be used to make the prototype, which was Delrin. It has a yield strength of 63 megapascals and maximum von Mises stress of 21 megapascals. The simulation was done by creating a pressure study where the bottom of the plate was fixed and an internal pressure of 100 psi was used with a factor of safety of 3. The results of the analysis clearly showed that the air bearing would be able to operate safely in the operating compressor pressure, which was 155 psi, as the maximum von Mises stress obtained from the simulation was 20.6 megapascals. Bolted connection on the air bearing was tested using the Smart Fasteners tool in SolidWorks, and the material for the bolt was selected to be a non-ferrous material, which was aluminum 6160. The simulation results were validated as seen in the pictures, each bolt appearing green. Lastly, the bolts were checked for failure in static operational condition and it was found that all the bolts were okay and functional. We will now show you a video comparing the old air bearing setup's performance to that of the new setup. As it can be seen in the video, the new air bearing setup allows for a much smoother testing experience. It provides more than enough airflow to generate adequate lift under the hemisphere housing. The increased tank capacity of the new air compressor also allows for several minutes of test time at once, compared to the old setup's time frame of approximately 20 to 30 seconds of quality testing. Using the test matrix shown, the previous weight achieved for the original bearing design was 7.74 by the original ADCS test team. The new bearing plugged into the same matrix now scores 8.84.
The team was initially going to have to design and build a support structure to hold the air bearing, but Andre Pan, another member of the Kilik 1 team, was kind enough to design and build one for us out of spare material he had from another project. It is built using only non-ferrous materials, as can be seen from the video, is sturdy enough to keep the bearing steady during testing.
The internal support structure is used to balance the system suspended by the air bearing. This refers to the satellite, the internal support structure, and the acrylic hemisphere. It was designed and fabricated to be made entirely out of non-ferrous materials so as to not disturb the magnetometer readings. The materials were plastic, aluminum, and brass. The hemisphere configuration will give it complete freedom of rotation about one axis and partial freedom about the other two. The final design of the internal support structure was picked via a scoring matrix where it scored the highest amongst the other options. The current design proved to be much more user-friendly, light, cost-efficient, and stable. Afterwards, the design was then further refined to optimize its components and make them easy to 3D print, post-process, and assemble.
So there were a total of 24 system requirements for the ADCS. Out of the 24, 12 were satisfied by the simulation, 8 were satisfied by the design itself referring to manufacturer's data sheets and unit testing in the future, and 4 were satisfied by virtue of the other 20 being satisfied. All requirements have been accounted for, and several requirements have redundancy in their validation method. For example, some are validated by design in the manufacturer's data sheets and also in simulation. Out of the 24 key requirements, 8 key requirements are summarized here. Out of the 8 key requirements, 5 were satisfied by simulation, where the other 3 were satisfied by design or unit testing. For instance, the first requirement, that Kilik 1 should perform the detumbling stabilization within 24 hours of launch, was verified by simulation results, in which the detumbling of the CubeSat was completed within 35 minutes of activation. Similarly, the simulation results also verified requirement 2, SYS-ACS-021, by showing that the CubeSat detumbled to a spin rate of less than 0.25 degree per second. However, requirement 3, after detecting an anomaly, turn off actuation but maintain attitude determination on, was verified by the inbuilt features of the module where certain input commands allow functions to be enabled in CubeSat, and this is also to be tested by the ADCS testing team prior to launch. Similarly, the remaining 5 requirements were either validated by simulation or are to be validated by testing the built-in design features prior to launch. It is also important to note that the simulation accounted for all the possible disturbances such as sensor noise, gravitational gradient, aerodynamic drag, and magnetic moments from currents in the solar panels.
The first step of the ADCS testing phase is the verification of health and performance of individual components following the health check guideline provided by CubeSpace. There are checklists in the guidelines, and by following the steps of various experiments, some as simple as simulating the sun with a modified desk lamp, various data values are to be matched with the ones provided by the manufacturer. This is an important step because if any issues are noticed during this phase, the CubeSat team would need to contact CubeSpace regarding the production faults in the components. The second phase is the testing of the ADCS module subcomponents integration, control algorithms, and estimation algorithms physically. This would be done by simulating a space-like resistance-free environment with the help of the air bearing, which was made in-house. A 3D printed structure with the ADCS inside would be placed on the air bearing to conduct testing such as detumbling and its ability to maintain attitude. This has already been verified by virtual simulations, so the physical testing will aim to gain understanding of the real-life working conditions of the ADCS system through binary testing, and allow the team to get familiar with the purchased module. This will also be helpful for the integration of other subcomponents as well. It is important to note that all of the components developed in-house are strictly for testing purposes only, and none of it will make the actual flight model.
This is the setup for the air-bearing testing. It consists of several parts. First, a minimalistic satellite will house the ADCS module along with the minimum number of components required to sustain its operation, in this case a battery for a power source, and a microcontroller unit to serve as a mock on-board computer, all held together in a frame. The minimalistic satellite will be fixed to an acrylic hemisphere via an internal support structure that will balance the body. Then the satellite inside the support structure will be placed on the air bearing, and compressed air will be blown from the bottom, suspending it. The smooth surface of the acrylic hemisphere suspended by the cushion of air created will eliminate friction and allow for complete freedom rotation about one axis and partial rotation about the other two. The attitude of the ADCS system as part of this arrangement will be recorded and analyzed by the motion capture system available at the university. First, the engineering ADCS module will be tested in this setup and then the flight model. This is a table with the hardware that needs to be purchased, built, or assembled for the ADCS test plan. Currently, several items for the ADCS test plan are already finalized or under construction. The air bearing and the internal support structure have been finalized. There is a picture of it on the right, whereas the minimalistic satellite still has a lot of work to be done for it.
The document package that will be handed over will include a general handover document. This is intended to ease the transition of the incoming group, getting them up to speed on everything that has occurred and what needs to happen next. This handover document will include a general KILIC 1 project overview. This overview talks about the KILIC 1 members, supervisors, graduate students, contact people, and the subsystems of the satellite. This is just to give an idea of who's who and what they are in charge of, as well as to whom they can reach out for help. Next, the relevant repositories section will talk about where they can access all resources and information. This includes the ADCS test team's drive, the KILIC 1 group drive, and the GrabCAD to access most CAD models and assemblies. Next, the ADCS test team's chronology will go over what has occurred so far. This includes the design we have considered and the important decisions that have been made thus far, such as deciding not to pursue the construction of a Helmholtz gauge and buying a simulation software from CubeSpace. This section also discusses the feedback ADCS received during important technical review sessions with the Canadian Space Agency. Finally, a section that outlines the subsequent steps in the project will be introduced. This section will let them know where they'll start off from and what their scope of work is. So in the next term, they will mostly work on getting familiar with the purchased simulation software and developing the minimalistic satellite. If time permits, they can look over into expanding on the design of the internal support structure to have a full sphere configuration. Thanks for listening. We will now take any questions.